So a while ago, I was scrolling through Kaggle datasets, and I found out this. I found out about this dataset called medical cause personal dataset, and it's essentially about predicting the medical charges of an insurance company based on certain attributes of the person they are getting the insurance for. So there are some details over here like the age of the person, the sex of the person, BMI, and stuff like that, number of children the person has, whether the person is a smoker or not, the region of the person, and then the actual charges. What you're supposed to do is to essentially generate the charges that someone is supposed to be based on the person's features that are listed over here. So I took on this challenge to actually work on this. I actually finished it a while back, but I didn't upload it early, so it's not that I'm making a video on it. In this video, I'm basically just going to walk you guys through the whole process that I went through to try and create a model, machine learning model that's able to do what I'm supposed to do, which is to predict the insurance charges based on those features. So we are going to go through some data exploration, and after that we'll try and process and do feature engineering of the data set. Then we are going to try and build our model, get an evaluation step, and then try and tweak some parameters to make our model better. So I've already written the code, so I'm basically just going to walk you through what I did. So we're going to be running the notebook one by one. Alright, so let's get started. So these are some dependencies that I've imported. These are just some configurations that I give my Seaborn. This is actually the first time I'm using Seaborn. Configurations I give my Seaborn in terms of the styling of the graphs that it's going to plot, essentially. So now let's go ahead and load on our data set, and then we try and get some information about the data set. So here, the data set is sort of clean because it doesn't have any null values, or that's the most important thing I'm looking at, and it seems to be set for you to actually work with. So you don't need to do much of data cleaning over here. So it's kind of an easy data set to work with. And what I did from here on is to just do data exploration and visualization to try and understand the data set that I'm working with and the features that are more important and the ones that are not important. So first of all, I checked the value of the regions. So obviously the regions are not going to be a continuous data points. So I have to check how distributed this region is, and by the look of things, it seems to be very evenly distributed, as you can see. So I first checked the value count of each of the regions: southwest, northwest, southwest, and the southeast. So we have this, and I basically plotted that with Seaborn, and as you can see, based on this, it seems to be a bit balanced in terms of the region, even though southeast seems to be a whole lot more than all of them. If you consider the difference, it's not that much. So there isn't any bias based on the region of the person. Then I also tried to explore the sex of the person. Let's run that and see how balanced the data set is, whether maybe it is skewed towards the females or the males. But then based on what I'm seeing over here, it seems they have almost the same number of males as the same number of females. So that is also not something that's biased. It's not something that would affect, for example, our train test split. For example, maybe I'll end up splitting it and it won't go according to this ratio, but then there's nothing like that. Then I also wanted to check whether the person is a smoker or not, that column, to check how distributed it is. And this way things got interesting to me, because I realized that less number of the people were actually smokers and more of them were not smokers, which means that if I wanted to do my train test split, the thing that came into my mind over here was that I had to use stratified splitting, so that I won't just split randomly. I will split according to this ratio of smokers and non-smokers, so that the train test data sets should reflect this ratio. And I went ahead to do that. We're going to look at that in a sec. And this is actually the data set. I just having a look at it in the middle over here for no reason, actually. Right, so after doing that, I also tried to see the distribution of the BMI of the people, and I wanted to check the distribution of the BMI of the people with respect to whether they are smokers or not. And also based on this, it seems to be a bit more evenly distributed, because if you look at those people that are not smokers, the distribution of their BMI is essentially close to the distribution of those who are actually smokers, the BMI of those who are smokers. So here too, there isn't much of a difference. But then all this data exploration is doing is to give me insight into the data set that I have. Then I also went ahead to check the distribution of the age distribution of the people based on whether they are smokers or not, and that also seems to be evenly distributed. Like, age distribution of those who are smokers is really close to the age distribution of those who are non-smokers. It's just the number of smokers that is less than the number of people who are not smokers. Apart from that, there isn't really much over there. Then I tried doing a correlation plot over here to just check how the columns are related to each other. And looking at this very carefully, you realize that the highest correlation that I actually got here was 0.3. And looking at the charges column, the charges is sort of like related to the age, positively related to the age. So it's as if as the age increases, the charges also increase, a bit, like some sort of a bit. And there's also a little bit of correlation between the BMI and the charges, but that doesn't really like ginger you to say that, oh, they are very, very much correlated, and as such this would affect this that much, right? So I tried doing a pair plot of that correlation just to show the graph of how like everything is. And as you can see, this is how the age and the charges are. So the age and the charges, you can see that there is that kind of positive sloping nature of the data points, just to tell you that, oh, as the age increases, the charges increase a bit, that kind of idea. And it seems to be the same way for the BMI. But if you look at the BMI, it's only those who are smokers that have their insurance being higher as the BMI increases, their insurance cost being higher as the BMI increases. As you can see, the I don't know if that's violet or something. The yes, which is violet, representing the violet, which is representing yes for smokers. It is that which tends to like increase, have a positive slope as the BMI increases. But then for those who are non-smokers, it's sort of like evenly distributed. And it makes sense, because if you are a smoker and you are old, by the time you are old, your lungs are probably destroyed or something. They are damaged, so you won't really be able to like have good functionality of your system. So you require more medical attention. As such, your medical insurance will be like more costly. Like, that makes sense to me that there is this kind of relationship over there, and like it's a really great thing. So if you also look at something, you see that smokers have a higher cost compared to the non-smokers, because you'd see here that in the charges row over here, those that are smokers, the violet one, are sort of like above those that are non-smokers. So it tells you that the insurance cost of those who are smokers is actually a bit higher than those who are not smokers, generally. That's the insight that I got from that. Then I went ahead to do some data, feature engineering, just to make sure that my data is set. So like what I did initially, the initial thing that we just talked about was just like looking at data set, trying to get some insight of the data set, and through the insights, being able to like get some, idea of how I'm going to approach the problem. And I think that did, I learned about the fact that I have to do stratified splits for the train test split, so that I'll be able to maintain the ratio of the smokers and non-smokers. Like, that's one of the most important things that I learned, and I really like it. So next step is to do some feature engineering, and that isn't really much. Now, when I look at the data set again, I wanted to basically, change the charges. They have some decimal places over here making a float. I literally just changed them into an integer. So I applied the int function to the whole of that column, because I thought it would be easier to just predict the integer value of the charge instead of trying to predict the decimal places also, right? Then initially I tried to actually categorize the BMI of the people. If it's between 0 to 18.5, I would say that they are underweight. If it's between 18.5 to 25, I would say that they are, it's a normal BMI. If it's above 25 and goes to 100, I would say that it's the person's overweight. But then after doing this categorization, I realized that it rather made the performance of the model worse, so I didn't do that. I'll put a link to that in the description and you can go ahead and check that and run it for yourself. So here we have changed the charges into integers, and when you look at that again, the charges have turned into integers now. Now in my model building and evaluation, you have to like import the necessary stuff. So like I was saying, talking about stratified splitting of the data set so that the ratio of the smokers and the non-smokers would be maintained. Yeah, I did that here. So I basically imported a stratified shuffle split, and using my training index and like using a for loop, I was able to get a training index and the test index from my data set after splitting it here. The number of splits has to be 1, the test size 0.2. I added a random state to make sure everything is constant. Then just some usual Python stuff to make sure that I get the actual X train and the Y train, X test and the Y test over here. So this is the state that I used to actually split my data set into the training set and the test set. Now I had to write a function to help me evaluate the model. I was going to try out a lot of models, and I didn't want to have to like write the same evaluation step for each of the models that I tried. So I put it into a function where I basically passed that model to that function, and NumPy and the rest of the things that I used, the sklearn metrics, I'll use that to like print out some metrics of that model. For example, I'll do a prediction on the test set, then I'll print out the squared error, mean squared error, mean absolute error. I'll print out the R2 score, which is actually the major thing that I am using to score this particular that I'm using to score models on this particular project, the R2 score. So I also do a scatter plot of the predictions and the actual data points over there. I'll show you how that looks in a sec. Yeah. So let's go ahead and run this and make sure that we are good to go. Now when it came to the model building, I had to do some data transformation and make sure that I do some scaling and stuff like that. So what I did was I first use an encoder to make sure that the sex is encoded. Machine learning models work better with numbers, and if you give it something like male, female and stuff like that, it will be difficult for it to recognize. For example, if I were to go to, let me show you something here real quick. So if I was to do insurance.head here, and you come here, you realize that the sex is either male or female, right? And whether the person says smoker is also yes or no. Region is also like written in it's written as strings, but machine learning models work best with numbers. So what I was trying to do over here was to encode those strings so that they are turned into numbers, and I use one hot encoder for that, which is essentially like a binary sort of thing. If it is male, I write 10. If it is female, I write 01, that kind of thing. You can go ahead and look at that. Then I use the scaler to scale the numerical values inside the data set, which is the age and the BMI. Those are the important numerical values over here. The charges, we want it to be how it is. We want to scale them before. If anything else is there, we pass through, for example, the charges. Right, so I created a column transformer over here using that encoder and the scaler. Then after that, I had a list of models over here, which is I used the linear regression model, the rich linear regression model, and the random forest regressor with some initial setup essentially. Right, so I basically used the for loop over these base models and put that module and the column transformer that I have created into a pipeline. So it's basically a pipeline of doing this data engineering, changing the scale of the numerical values and encoding the non-numerical values, all of these steps. Then after that, it passes the output of that stage to the actual base model for training, and that is the pipeline that I've created over here, and basically fitting that to the X train, Y train, and then I call my evaluate model function to do the evaluation for me, passing in the appropriate parameters over here, and that works. So let's go ahead and run this cell and see what we get. So this is how the evaluation function works. It prints out the model name, the error, the mean square error, the mean absolute error, and also the R2 score of the model. So the linear regression model has an R2 score of 0.78, which is the major thing I'm using to score the thing. Like if it's more, you are better. And the more how I plotted this graph is that the more the spots, the dots, the scatter plot gets closer to the diagonal line, the better the model. So if you were to consider this model and this model, it's sort of close. But if you were to consider this model and this model, you see that this one has more data points being shifted close to the diagonal line, the red diagonal line, and that makes it a bit more better. That's like a good way of visualizing the performance of your data. Obviously not the performance of your data, the performance of your model. Jeez. Right, so I realized that out of the 3 models that I chose, it was the random forest regressor that was doing a whole lot better, 0.8458. So I literally shortlisted that model, and that's what I did over here. Shortlisted that model, which is essentially just writing the same pipeline thingy that I wrote here, but then specifying just that model straight here. Nothing so fancy here. So I shortlisted this model, and I wanted to tweak some parameters using the grid set to see if I could make it a bit better. So right now our R2 score is 84%, right? I wanted to make that a bit higher. So I was trying to tweak parameters over there. So it's a random forest regressor. Some parameters like the number of estimators, the maximum depth, and the mean sample split. Right, you can check out what all of this means in the sklearn documentation. Yep. So I wrote out some values for them just to make sure that everything is going on well. And this might actually take some time because there's a lot of combinations of these 3. 1, 2, 3, 4, 5. 5 times 5, that's 25 times 3. That's like 75 possible combinations. So I basically trained different versions of the random forest regressor based on different parameters and try and check which of them will be best. That's what I did over here. Now you could literally look at the grid search best parameters by just looking at this, and it says that I should take a mass depth of 5, number of samples split 2, and the number of estimators 500. That was like the best of our models. And here I basically printed out the best 10 models and their scores and the rest of the details that are there, right? So as you can see, their rank, their mean test score, and a lot of things are here. Like all of these are there for you to have a look at, just to make sure you know the performance of your model. All of these are there. So right, I literally just said that the best model is the grid search best estimator, and I tried to evaluate that model again. So this is the state of that model, and you see it has an R2 score of 87%. Now initially it was 84, now it's 87%, and as you can see, most of the data points are close to the red line, the red diagonal line, telling you that the model is doing a whole lot better than the previous one that we saw. Right, so the grid search best parameters, as you can see, just repeating them over here, and I use those details to recreate the pipeline again as a final model, and I feed this one to the training set again. So yeah, essentially fitting the final model to the training set again, and I get the same thing. Here I try to fit it to a full data set. So I had X and Y as a full data set without an X train and a Y train, and see how it's going to perform. That's usually what you do on your final model. You want it to be better. So what you do is I basically combined everything. It's just the insurance or drop charges and then the charges over here. Then I fitted that model, the new model, to the total training, the total data set, not just a training and a test set, the total data set. I picked that model to read, made a prediction, and used that prediction to plot the necessary parameters that we were plotting. And as you can see, finally our model was able to get an R2 score of 88% on the full training set. And to me, I think this is actually a very good score. It is a very good score. Like, if you guys have a better way of solving this problem, better, not necessarily better, I want to actually see how you guys will tackle this problem. Just drop the link to your repositories in the comment section. I'll definitely check those ones out and see how you guys are doing out there. So I've been trying to learn machine learning for quite a really long time now, and I would say most of the time I'll be lazy, but I'm trying to pick up that this year. So guys, that's it for this video. This is my full process, the process that I went through to tackle these medical cost charge prediction problem, and I was able to build a final model that was able to get me this particular score of 0.87, 87% on the dataset. I think that's pretty good. I am going to leave a link to this repository which has the code here. I'm going to leave a link to this repository on my GitHub in the description. Guys, that's it. If you're new around here, join me, subscribe to the channel, and let's learn machine learning together. We're all learning. I'll see you guys in the next one. Cheers.